provided. We have 10 more feet of medium dense sand, so you can either enter the bottom of the depth if you're looking at boring, or you can enter the thicknesses, however you choose to look at that. Sand and value 25. And then you have clay, which is fairly stiff, and value of 30. And then below that you have sands with an end value of 50. So you have dense sands through the bottom of the borings. So okay, so at the top of this input, I have got the static capacity based upon my penetration. So I'm going to say that I've established all the soil parameters. Now I say my pile goes 5 feet into the ground. So now I have a whopping 8 kips of capacity. I have 1 kip of shaft resistance and 6 to 7 kips of end bearing. So I'm going to keep moving this deeper and deeper until I achieve my required 400 kips. So 65 feet in the ground does not cut it, although it's getting closer. 68 feet, getting close. 5. So 80 feet, I have 406 kips. So that's basically my static analysis, which I could have just done on hand or on paper, says that I need to go 80 feet in the ground to achieve the 400 kips. So curious, let's say I have 400. So 402 kips. So now I've got it dialed as close as I can to that required capacity. So 79 feet in the ground. So what I've not made considerations for are the dynamic parameters of the soil. So this is going to give you some recommendations. Within other parameters, it's going to say these are the recommended quake and damping values that I recommend for these soil types, which also accounts for their soil strength. So I'm not going to spend a lot of time trying to figure these out. I'm going to auto all parameters for all layers. So it's going to say your clay layers have a damping of 0.2 seconds per feet. Your granular soil has a damping of 0.05 seconds per feet. So if I'm doing that static analysis and this doesn't mean a lot to me, I'm just going to input those recommended values. The only time this could really get you in trouble is if you have rock or hard pan or something that's, like something that's a very dense cell hard clay where you don't know those parameters and you're going to have great effects on your results based on what you assume. So I have taken all the recommended values for these soil types, and it's given me my quick summary right here. So 44% of that capacity is coming on in friction. Those are the damping and quakes it's given me based on the soil types, as well as the size of the pile too at the toe. And now I'm going to give it the capacities that I'm interested in analyzing. So I'm just going to enter a few. So we need to achieve 400 kips. So I don't need to look at a big wide range of capacities. Congratulations, you're on the last step of creating a new project. It's sort of giving you a quick check right here of everything that you've entered. So if you entered everything correctly, this is where it flags if you have a major issue. Is that correct, Fruit?
It should, yes.
Like it would say you've not entered a helmet weight, which I've seen wave equations that have no helmet weight. It makes a lot of sense. So it's gonna ping you if it doesn't like what you've done, but walking step 1 to 2 to 3 to 4 usually takes care of that. So now we've got a full analysis ready to go. So I'm going to analyze this data, this driving condition. So your limit, the Minnesota DOT limit's 180 blows a foot. As I get to 400 kips, my blow count goes to 1,600 blows per foot. So basically this is telling you, this D19 with this pile, length, thickness, you're crapped out at 350 kips. You're not gonna be able to get more with this hammer. So this tells you that this hammer is unsuitable for the 400 kips capacity. Your stresses, your predicted stresses in the pile are 35 KSI, so well below, I assume you're gonna probably have grade 3 pipe with a yield stress of 45 KSI. So the D19 is no good.
So Travis, is there a way to go back in and play around with the numbers?
Or hammers, I've never done more than 2 or 3 basically. So I'm gonna try a D30, the next common size up, right? D25s are around, but I would really call a D30 the next common size up from a D19. So I'm gonna assume that they've dropped their D19 out and they're putting the D30 in the same leads and they've got the same helmet cushion material properties. So now I'm gonna run this again, and now it's gonna run the D19 as well as the D30. So here's the D19 results you saw. We cannot achieve the 400 kips. D30. Okay, our blow count is 50 blows a foot, so this is looking pretty good. Except now our stresses are in excess of the driving stress limit. So, like I said, I'm assuming you're gonna have grade 3 pipe with a yield strength of 45 KSI. Specs limit driving stress to 90% of that for a steel pile. So we need to show that this can get within 40.5 KSI. So we're measuring a stress slightly in excess of that at the top, but the maximum at some other point in the pile is 45. So that's past the yield strength. So this is not good. So our D19 was too small. The D30 is too large. At least it's too large on the maximum hammer fuel setting. So let's try to cut the fuel down on this D30. So I'm going to select my D30, and I'm going to take it all. I guess I should have backed up. The hammer has 4 fuel settings. Almost every hammer does, with 4 being the maximum, 1 being the minimum. So that's how the wave equation is set up as well. So by default, you're running it at the maximum. Let's try it on fuel setting 1, or as they put it, maximum minus 30.
Have you guys tried to automate that to pick the right fuel setting?
Not really. And because there's so many different things you could conceivably change. But that's not a bad idea in trying to decide whether it's a fuel setting check or a wall thickness check or
capacity and get a range of strokes and blow counts. So a diesel hammer is not going to transfer more than 80% of the rated efficiency, right? Because a diesel hammer transfers 50%. When 55% is a really good hammer.
So go back one more time, Travis.
Okay.
And under your hammer parameters for strokes,
Let's make it fixed.
Start it at 6.
Yeah. Instead of letting it run a bunch of goofy things, you can do 6, 6.5. I should have done that. Thank you. So now we're looking at all the combinations that will achieve 400 kips. So 6-foot stroke, 300 plus blows per foot, stresses are fine. The opposite end, 10.5-foot stroke, blow counts are low. So this is essentially pretty close to what we saw in fuel setting 4. 48 blows a foot, your stresses are way too high. So essentially you can't go greater than 7.5 per these stress limits. And you can't go anything less than 7 per your blow count limits. So you've got a wide range of between 7 and 7.5 feet is where it's suitable.
But now, like your energies on the side, the next column over, is that the energies? The ones that's not on the screen.
Yeah, scroll over.
Yep. Scroll.
Drag it from the bottom.
So that chart shows the D19?
Yeah, that's just the title of the file. That's because I started with the D19, so I typed in all the description.
We don't have max.
So here's your energy transfer ratios. So this is fairly, what I said is almost true. So at your maximum strokes, this is predicted with default energy efficiency reductions that transfer 65% of the rated energy of the hammer. When it's down here at 6 foot stroke, 37% of the hammer. So that was showing how we would select a hammer for a given soil or a pile type and pile capacity. Outputs available within WEAP. So if you look, you've got 3 standard outputs. You've got a summary report, which is very short, a standard report, which has got 6 or 7 pages. The numerical output has everything that models makes up that model. Fortunately, the numerical output's maybe more confusing because it has so much information. So I have these little cheat sheets, which I will give to you if you like. But so this is your summary report. So you have 2 pages of output. Standard report, 6-7 pages. Here is what I wanted to show you. So if I was reviewing a wave equation, this summary report is almost enough information, not quite as much information as you like, but I've got all these color codes of what parameters you're checking on this output. So for your hammer, there's the hammer, there's the weight efficiency, the weight, the helmet weight, the cushion. This pressure would be the fuel setting. It's not straightforward, but fuel setting 4 is 100% pressure. If you reduce the fuel to fuel setting 1, it's 80% pressure, 72%. I can't exactly remember the number. But you can see that they reduced the fuel setting here. There's your efficiency, of course. So if you have a battery, you'd like to see some reduction in efficiency. Soil parameters, this is the part that you guys are rightfully concerned with. So here is the resistance distribution. So 44% shaft resistance in this case. Here's your dynamic soil parameters, which you could check against the recommended values in the WEAP. Pile length, so total pile length, pile penetration, the area, that would be the section that you selected, and then here's your output. And if you go to, I thought I had a different, I thought I have the same thing, because I didn't put it on the slide, but for a standard report, I've got the color coding for each of these different parameters as well. So I'll give those to Joe. You can,
different plates, Joe.
you can take it. I got some.
You did.
You can check. It'll be a guideline as to how to check that your WEAP is complete. So like I said, if you see a WEAP and it has helmet weight of 0, then you know someone has done something incorrect. It's very easily, if the area doesn't match the cross-sectional area of what you specified, then you know you've got a big problem. So this gets you a long way to checking the validity of the wave equation.
And we should never be seeing a hammer efficiency of 0.9.
Yeah, I don't. Can you? I don't.
The only time that would be is if you had like an IKIP or IHC hydraulic hammer or a Mank hydraulic hammer or potentially some of the Gentons with the do use the impact velocity, but not a diesel hammer.
Diesel hammer, yeah, they should. you know, the pressure could range from 100% to lower for the fuel settings, but that efficiency should not be touched.
So
unless-
the double acting diesels, are they,
I think it says that efficiency is default is 0.8 as well, but
Yeah.
I never see them, I don't know.
oh, but they're not used for nice.
Yeah, we don't, we see them for Becker penetration testing occasionally in the west. That's kind of a SPT, but for bouldery, gravelly type soils, we're looking for strength out of that, but I haven't seen it double acting diesel in a long time either. Still make them apparently, so somebody must use them. X-axis, once again, is time. Y-axis is force and velocity. So red curve in this case is force, blue curve is velocity. We're looking at 102 milliseconds worth of data, so these things are over in the blink of an eye. Very quick. And so first thing I like to do is check the force and the velocity curves before the impact. So remember, the impact is really starting where this abruptly rises. Right here at this dashed line and right there at that dashed line. And so looking at the top, this is an H pile driven with a diesel hammer. On the bottom, we have a pipe pile driven with a steam hammer. And really the difference that we see in the early portion before the impact is the steam hammer is quiet. It's zero. And the diesel hammer is gradually increasing. And so at a glance, without knowing what type of hammer I'm looking at, from the PDA record, we can tell if it's a diesel or not. And so looking at the diesel, remember Travis, in talking about wave equation, described how we model the pre-compression phase of a diesel hammer. And those ports close off, and as that ram starts to fall, the volume of air trapped, or the amount of air trapped inside that pre-compression chamber is fixed. The combustion chamber is fixed. As the ram gets closer and closer to the impact, the volume is getting smaller and therefore the pressure is going up. So that pressure is pushing against the ram, but it is also pushing down into the pile. And so when I look at it going down into the pile, this gradual rise is indicating the compression of that air. And in very easy driving cases, sometimes that pre-compression can actually do work to push the pile into the ground. And so we see that this force does have an effect on things. So before the impact, if I look here versus here, I can get a relatively clear sense as to whether it's an open-end diesel hammer or not. Second, I check proportionality. Not wanting to come in curveballs and wanting to show good data initially, we are looking at, so that proportionality and the sharpness of that impact also kind of tell us a little bit about what might be going on with this particular pile. Next, as we kind of continue down the record, we can look for similarity in shape between the force and velocity. And so, they're tracking one another to this point, and then our force starts to separate from our velocity. Our velocity slows towards zero, our force is creeping a little bit upwards in this region, and we don't really see that on this particular pipe pile. So that difference is telling us what? We said that when skin friction arises, very good, when skin friction arises, the velocity slows down and the force tends to creep up. And so because it's happening before this indicator of the bottom of the pile, then we can see that difference in skin friction between these two different piles. So there's our shaft resistance determination. Next, we check for the toe behavior, which is coming in here. On one of them, we see for the H pile, which is during relatively early driving, we can see the velocity trending up and the force trending towards zero. When that force trends towards zero, that's an indicator of a free end. And so this is very likely a relatively easy driving condition. Where on the bottom, in this case, my force is very much doubling and my velocity is trending towards zero. So if the velocity at the toe trends towards zero, that tells us that we're closer to a fixed end. And so, in this case, I've got some shaft resistance, but not a lot of end bearing. In this case, I've got very little shaft resistance, but a whole lot of end bearing. And so this informs how we would interpret these force velocity curves. And then, if it is available, and I say if it is available, we have recorded it, but when we do CapWAPs, we don't always include it in our record. So sometimes we might cut it off, the record off somewhere around here, and that's done so that we can get detail, and we can see the detail in the early portion and important portion of the record. But if it's available, it's worth checking the end of the record to see that everything goes back to zero. Because the assumption, the very basic assumption of PDA is that before the strain gauges and accelerometer is triggered, the pile is at rest. And at the end of that impact, the pile is at rest again. It might only be at rest for half a second, but it is, at the end of these records, it is unstrained and it is not moving. And so when we start to get to some of these pneumatic hammers that we see for like guardrails and solar panel farms, where they're driving piles at 300, 400, 500 blows per minute, that's where we may actually get multiple blows in the record that we keep. And then that becomes a much more difficult thing to analyze. But generally speaking, up to about 200 blows per minute, which is most double-acting diesel hammers and most hydraulic hammers, we see that there is enough of a quiet period before the next blow that we can analyze things well. A drilled pile with a drop hammer, we can also, again, we check before the impact, we see it gradually rising. That tells us it's a diesel. On the drop hammer, we see it's all zero, so that tells us that it's not a diesel hammer. Proportionality, again, looks pretty good through this region. Looks okay through here, and then we start to get about a quarter of the way down a significant indicator of either resistance or a bigger pile section. For driven piles, we don't really worry about that. We don't worry about the cross-sectional area of an H pile changing. But for a drilled pile, that is very much a concern, because in cases of auger cast piles, they pump them under pressure sometimes into soft soils. And so as a result, we get bulges and we get necks and we get other things that we need to think about. And so next we check our proportionality. Again, pretty good through here, pretty good through here, and then we see a lot of resistance. We check for our similarity in shapes, and generally we kind of have those. Looking at the differences in the impact on the concrete pile versus the difference in the force impact on the drop weight. And the drill shaft, typically drill shaft tests look much smoother, and they take a longer period of time to reach a peak because they're relatively heavily cushioned and the rams are pretty heavy. But if we take a look at our pre-stressed concrete pile, we still see that those impacts are a little wider than what we were seeing for the steel piles, because they're cushioned with additional plywood, and as that cushion stiffens, it becomes a sharper impact, but initially it also has this kind of wide pulse that we would expect. Again, checking for separation between force and velocity. Not a lot of shaft resistance here. A lot of separation between force and velocity in this on this drill shaft on the bottom. In fact, we have a velocity that drops negative prior to the reflection from the toe coming in. And when we do that, a negative velocity means the pile is moving in what direction? Up or down? Up. So it's starting to rebound even before we're getting information back from the toe. And so in that case, we may have scenarios where shaft resistance is starting to be no longer mobilized early, but then later mobilized late. Looking for toe behavior, again, our velocity gets very high and our force drops to 0. Is that a free end or a fixed end? That's a free end, very good. And here we see the velocity is well below 0, and the force is trending down towards 0. It's not really consistent with either a free end or a fixed end. Instead, that's probably a scenario where not a lot of movement is getting down to the bottom of the pile. Going back to the mobilization question that was asked earlier. And at the end of the record, clearly the drill shaft has gone back to 0. This one probably could have kept a slightly longer record to make sure that that happened on that. So, a question that came up earlier, why do we do 2 strains? What should we do for 2 strain gauges that maybe on a batter pile or on the top and the bottom versus on the individual sides? We have 2 strain gauges, F1 and F2. Those are both included in the average. If we see both those numbers in the upper left, right, upper right, is this a diesel hammer?
Yeah.
Yes, it's gradually rising, so this is a diesel hammer. Is this proportional? Yes, it is proportional. Is there any shaft resistance? Yes. Our force trends towards 0, our velocity increases, and then we get a big reflection in force. That tells us that it's not a fixed end, but it's pushing into the soil, and then the soil is really starting to push back. So this is probably more consistent with something like a dense sand. When we look at the individual strains, we see that one is very low and one is very high, but on the average, they're matching each other, the proportionality, quite well. This is why we use more than one strain gauge, because on the average, it agrees nicely with what we expect it to. But if we were to only have one on the side that's getting hit harder by the misaligned hammer, this value would now be up here, and our proportionality would be go away. Similarly, if we only had that one, it'd be down here, and our proportionality would be not so good. So, but by using the one-dimensional theory, which says the whole thing on average is behaving as a one-dimensional wave, we can get a reasonable proportionality with the average, even in a case where there's quite a bit of bending and quite a bit of alignment. So, one time, in my misspent youth, I was out taking data, and I saw this, and my training kicked in, and I said, that hammer is not well aligned, and in fact, I can see it. So I told the contractor that maybe he should, make the hammer boom out, or to boom out a little so the hammer became more vertical. And he rolled his eyes and he did it. And then on the very next blow, the red line was up here and the blue line was down there. And so the act of trying to correct the bending actually made it go in the other direction. So instead of fixing the problem and making it perfect, I just wasted everybody's time. So as the PDA tester, if you have this, you don't necessarily worry about this unless the numeric value of that peak is really starting to go above the yield strength of the file material. And then, even with very large bending, our two velocities tend to be similar. And so, again, we always recommend a minimum of 2 strains. Because of this similarity in acceleration, we can get away with just one. But we always need 2 strain gauges to measure the force. And of course, we recommend 2 of each, so that we can always. Looking at the section just before the impact, is this a diesel hammer? No, it's flat. So looking at this, we can pretty easily tell that it is than a diesel. Looking at my pile information, my area is 1600, so it's a 40 by 40 centimeter pile, which is what, 8 by 8, I guess, if I've done that right. And then the modulus, specific weight, and wave speed all tell us that it's concrete. I apologize for the metric here. So this is a concrete pile. Continuing on, at my peak, do I see any proportionality? Are the force and the velocity similar in this case? Well, the velocity is way down here, the force is way up here, and I see this hump in the wave up that would normally indicate something so close to the top is a bulge, and an increase in the cross section, and probably not resistance. So something doesn't look quite right here. If I were in the field, I could look at the warning that sits at the top, and that tells me that the two velocities are not in very good agreement. If I look at the individual forces, they actually look more similar than the previous slide. If I look at the individual velocities, one of them is of a similar magnitude to these forces, and the other is coming in quite low. So, what's going on? Well, if you see this in a report as the DOT, you should call it out and say, why is this here? I'm driving through a peat bog, and you're telling me that I've either got a lot of resistance or there's something unusual about this particular pile cross-section. And so this is low. So if I look at that peak versus these peaks, they're similar. So I could turn off the V1 section, because when I look at this accelerometer, it has been rotated. So, SPT, one of the common things that happens with SPT tests is people only use it once a year, or once every 2 years. And if you're not careful, you can put the accelerometers on upside down, with the wires sticking up. And in that case, instead of positive velocities for downward motion, you'll get a very negative velocity for downward motion. And that will then make everything look kind of funny. So the direction of the accelerometer matters. If you put it in line, you'll get something like this. If you get it so that it's now rotated, you'll get a cosine of the angle that we're showing. If it's perfectly horizontal, it'll be 0. If it's upside down, it'll be exactly negative. And so in that case, during driving, the easiest thing to do is just turn it off. Or just to have them turn it off. We talked about wave speed, we talked about timber piles. If we want to determine the wave speed for concrete and timber, again, looking here, we see not a lot of change in force and velocity, so that is not a diesel hammer. Our peaks are proportional to one another. Up to about this point, our wave up is 0, and then we see separation between force and velocity. This is an indicator of resistance. Wave up is the accumulation of resistance over time or with depth. And so this is telling us that we have very little resistance in the upper 2/3 and then considerably more down in the bottom. Our force drops, our velocity increases, so the pile toe moves, and then things go back to 0. What we are looking for when we don't know the wave speed of concrete or timber, or when we are looking for the damage to a steel pile, we have our impact, and we expect this increase in velocity, this drop in force, and this increase, or this drop in the wave up, to be the indicator of our pile length, and to for this line to be more or less lined up with that. If it's not, then we can go back and make adjustments for the actual concrete or timber pile that we're looking at. we'll be looking at this a lot more this afternoon. For total damage scenarios where things are starting to become a lot. This is the same pile. This is the peak and the rise. We can see from the rise that the force is dropping, the velocity is increasing, and the wave up is dropping off. So rise to rise makes some sense. There are a lot of peaks here. This goes back to one of those can splices that we had talked about over one of the breaks. In that case, we're starting to see a little dip in the wave up, which is indicating a reduction in cross section. Soil resistance doesn't look like this. And because we've now got a little gap in there, it's having a problem, it's opening the gap instead of transmitting tension up, which is why we have that long flat section that's happening. Any follower drives that are happening in Minnesota?
Rarely.
Rarely? Good. Makes life easier. If you need to drive a pile below ground level, or drive a pile in the water to, say, the mud line, this is one way to do it. Again, we have our pile that's being driven. Once we get to the point where we can't drive on it anymore, they'll often pull out a piece of steel pipe or some special made follower. And ideally, you'd like the impedance of the follower and the impedance of the steel or concrete pile that you're driving to be the same. Why is that? Well, to the wave, if it is traveling in material of the same impedance, it won't reflect. And so we won't see a loss of energy, or a very minimal loss of energy if the impedances are the same, because the wave's just going to keep passing right on through. If, on the other hand, that impedance gets is much bigger or much smaller, then that creates a place for a reflection to occur, and that robs you of some of the energy that's going into the pile. So let's think about problems. One of the problems we just looked at was a velocity sensor that's kind of on an angle. Generally speaking, our problems come from bad cables and bad attachments, occasionally from bad piles, and sometimes just bad luck, in that no matter what you do, you can't avoid what's going on there. But the big ones are cables, sensors, and attachment. So how do we spot those problems? And again, this is thinking about it in the case of someone who is getting some data and doing a cursory review of data or a deep review of data for a particular project, particular for test piles. So when we look at that, the first question is, if the data is not proportional with that impact, how are our calibrations? Is our wave speed correct for concrete or timber piles? Is our pile very non-uniform? Are the transducers right near the ground? Because if you are doing a restrike at very high resistance, remember that soil resistance causes force and velocity to separate, and we may get that almost immediately. Is there pre-compression for a diesel hammer? Is there a long rise time? All of that is reasonable reasons why the data may not be proportional, but is the data consistent from blow to blow? That's something that's not so easy to do in a review scenario, but it's very easy to do when you're looking at the actual data files. Are the results not reasonable? Sometimes the calls I get are something to the effect of, my forces are 10,000 kips on a 12.75 inch pipe pile. What's going on? It's saying that my stresses are good, but my forces are very, very high, and so are my capacities. This doesn't seem right. And usually the answer there is they've inadvertently entered the full cross-sectional area of the 12.75 inch diameter instead of the wall thickness area. But unreasonable results often point out problems. In that same scenario, the energy is probably at 200 the rest until we can figure out what's going on. So if we look at the individual forces, we see the blue second force is very nicely of a similar shape to the velocity. But our force 1 is very spiky and has very high frequencies in it. So something is wrong with F1. Because of the bending, I can't turn it off. Because the potential for bending is occurring, I can't turn it off. So this data is then unusable. Because if we do that, then we run the risk of over or under predicting based on that bending. What do you think is wrong with that? Any ideas? That's a loose strain gauge. That means, remember, strain gauges have 2 bolts. It's very easy to under tighten 1 bolt, and when you do, that's kind of what it looks like. Same idea. Diesel hammer?
No.
We got gradually increasing force and gradually increasing velocity. So that's a diesel hammer. Is the force and velocity proportional? No. Not at all. In fact, anytime you see the force go very negative relative to the velocity, that's usually a problem. So once again, when we look at the individual forces, the first F1 looks good, but the F2 has this very high frequency and kind of up and down status that looks really like the acceleration. Again, in this case, that F2 is loose. Most of the data problems that I see, particularly on concrete piles, but also on pipes and to a much lesser extent H piles, is a loose strain gauge. And again, unfortunately, you got to recollect the data if that happens, or have them go recollect the data. Again, be safe and don't let the hammer keep running while you're tightening the bolts. We've seen that happen a few times in some of our data sets. It's not worth it, I'll say that. After we tighten the bolts, still a diesel hammer, our proportionality and shape of the curves are now similar. That separation is likely happening because of resistance. We've got some bending, but generally speaking, the overall shape of this curve looks much more consistent with the velocity. It's telling us a lot of shaft resistance. The velocity is moving up, the force is moving down, so there's some toe movement, and then we've cut it off before we can check if it goes back to 0. How is the proportionality on that one? I'm just giving a parade of bad data here in the hopes of some of it sinking in. So not good. We can see our force is doing this kind of double hump thing, and our velocity is jumping above it. We might initially expect the forces, certainly good to look at those. We look at our warning of our velocity. It says that it's low, so we take a look. And we can see that there is 2 very different velocity curves. Remember, they should be the same. So when we look at this, we are seeing that one is sharp and very much in the same shape as our red force line. The other is delayed, has a much higher peak, and is looking like it's kind of moving around. So V2 in this case is loose. What's happening? So remember, our accelerometers, you're sitting on 1 bolt. And if that accelerometer has some slop in it, if I put a bolt through that hole, the bolt moves with the pile. But if the accelerometer is loose, it's just going to sit there. When the bolt hits the bottom of that accelerometer, it's going to yank it down. And that yanking is this sharp increase there. What can I do in this case? Could I still salvage this data? turn off V2, perfect. So if I turn off V2, I can use one of the strain gauges, and life gets easier. If I turn off the sensor, or have the PDA tester turn off the sensor, then my proportionality gets much better. We haven't really talked about it yet, but the PDA also gives indicators of damage. And those indicators happen when the wave up abruptly drops down, which means when either the force abruptly drops or the velocity abruptly increases relative to the other. So I'm getting a damage indicator here. This is not a diesel hammer. Proportionality looks very good. Everything else looks pretty good, except I've got this big spike there. And those types of sharp spikes are not usually indicators of resistance. Resistance is smooth. And so when we look at our individual sensors, we don't see the spike in F2, but we do see it very sharply in F1. And so again, that's a scenario where you want to ask about what's going on with this data set. So this is a problem with a wire in all likelihood. If we look at the second data damage indicator, there we see our force dropping off and our velocity increasing. So that starts to look more like a free end. Remember, we said a free end condition is the force dropping to zero, the velocity rising. This is a free end condition that's happening early, or the beginnings of a free end condition that's happening early. And so this is an actual reduction in cross-section. And so that actual reduction in cross-section is likely an indicator of damage. When we get to 2L over C, our velocity goes to zero, and our force doubles. What does that mean? Fixed end. So we are at rock. So what's happening here? The pile was driven to rock, but we're starting to generate damage somewhere above it. Either because the rock is maybe a little sloped, or we're catching ourselves in the bottom of a boulder or something. So that one is correct. We see additional spikes 27 blows later. So the initial, so the F1 data set isn't getting better, but we also see that this small change is becoming a much bigger change, and the damage is progressing at the expense of a high reflection on the bottom. So instead of now being a fixed end, we're losing end bearing because we're scrunching so much and damaging the pile so much towards the bottom. For a hammer that's performing well, a uniform driving condition, the F and V should be similar from blow to blow. So once again, diesel hammer, good proportionality, separation velocity is increasing, force is dropping, so it's like a free end. Everything goes back to zero. If we look at consistent velocities, they're good, but on an adjacent blow, we see that one of the velocities accelerometers caught a spike of noise, and because of that, this accelerometer is not really returning to zero and giving us troubles. What do we do? What can we do with an accelerometer?
Disconnect.
We can turn it off. And so we can tell it to ignore that data set and just use the one for that single blow, or if it's happening on more than one blow, for others that are going on there. Looking at other trends of data quality, again, diesel hammer, good proportionality, but we see that the force at the end of the record doesn't return to zero. So what does that mean? We started with our two bolts of our strain transducer 3 inches apart, and at the end, they got closer than 3 inches apart. So that could be that the sensor slipped, or it could be that the pile is actually yielding. The two pieces between those two bolts got closer together for real. If we look at our individual stresses, these were as high as 64 KSI. This is at most 45 KSI steel, and so that's a scenario where we're clearly having an issue. So looking for data that doesn't return to zero at the end is also an important step in keeping an eye on resistance. Now, if this is 1,000 kips, so this peak force is probably on the order of 758 kips. If this is 10 or 12 kips, that's probably not so big a deal. But if it's 100, 200, 300 kips, then it's something that we worry about. And don't use data that doesn't return to zero on the force for the analysis. How do we fix the problems? Again, it's only something we can really do in the field that is similar to GRL WEAP, but instead of modeling the hammer, we're taking what we measured from the field and using that as our force and movement inputs for the numerical model. Any questions on choosing a blow? Any questions on reviewing data or the field aspects of seeing a PDA report before we move into signal matching? Oh,
How do you know if there's rebound in your pile or something?
yeah, that's a good question. Let's see. So a couple things, I don't have a good slide on this. I kind of do. So a couple things. If I go back all the way to the beginning on this drilled shaft, one way that you're looking for rebound is if in the velocity we have a significant amount of negative velocity. Remember, negative velocity is upward motion. In some scenarios, the pile will rebound, will compress, it will rebound, and the permanent set will be effectively zero. That happens in silty soils quite a bit. And so, if you're seeing, and remember, we take our acceleration data and we integrate it to velocity, and we integrate the velocity data to displacement. And so if you are seeing a displacement curve, normally, we'd expect the displacement to do something like this, where that is the permanent set. And the inverse of the set, so if it moved in 0.1 inches, that would be 120 blows per foot. So 10 blows per 10 blows per inch, or 120 blows per foot. If I had a scenario where instead of that, it does something like this, then if this were on the order of 2 to 3 inches, and this is 0, then that's an indication that you might be having a lot of rebound, and that all of the energy of the hammer is going into compressing the pile and soil, but nothing is achieving some failure of that soil. And so if you're on something like rock, well, there may not be a lot you can do about that. But if you think you're in a silty soil, then that often means that it's dilating. When it's trying to shear, it's dilating, and pore pressures are becoming very, very negative. So it looks like there's a lot of resistance there, but if you wait, then you can get through a point where that you can start to drive it again. Florida DOT has been doing a lot of work on this. They have a region in the northwest kind of area between the Panhandle and whatever's over there, Tampa, I guess, where they start to run into these very bouncy silt layers. And you get really high blow counts, really low capacities from the PDA that are borne out in static tests that are really happening because of the disturbance. And what that means is we measure the load, we measure the movement. The load is our strain gauge, the movement is our accelerometer. What we don't know is the system. And that system is the distribution of static resistance forces, dynamic resistance forces, and stiffnesses that are distributed along the pile. So remember, for WEAP, we used the geotechnical analysis and the soil type to try to figure that out, right? We said the resistance distribution along the shaft and at the toe comes from a calculation based on what we saw in the field from in situ testing, or just the soil type. Here, we're saying we're going to model those independently and match it based on what we observed instead of relying on the geotechnical analysis. The geotechnical analysis gives us a place to start, but we need to be willing to shift that around a little bit to match what we've measured in our construction site. And so the way that we work this, we set up a pile and soil model numerically in the CAT-WAP program. We apply the measured downward traveling wave. Remember, the downward traveling wave comes from the hammer. That's our input. That's our input load, effectively. That then allows us to calculate forces inside each 1 meter element of the pile, and it allows us to determine movements at those points from that force and the movement. We can calculate a computed wave up curve. Remembering that the wave up is the accumulation of resistance over the length of the pile. We then look at the computed wave up and compare it with the measured. So remember, we're measuring force and we're measuring velocity. And so we could input force and match velocity. We could input velocity and match force, or we could input a combination of them in the wave down and match the wave up. I like to do wave up because it is, you can directly determine things about the resistance. And you can directly interpret things about the resistance. That's pretty handy. If the computed and the measured don't match, we make adjustments to our shaft resistance and toe resistance models. And then we apply the measured wave down. And from our measured wave down, we calculate a wave up, we compare it to the measured, and we make adjustments again. And we iterate that several times until we can't get any better. At that point, we just move on. So the way that this kind of looks, our black curve is measured, our red curve is computed, and initially, our red curve may not look anything like the black one, and so we need to make some adjustments. Wave up is the accumulation of resistance, and we often see this little tensile dip that happens at the pile toe. So from here to here is shaft resistance, from here out to here is shaft resistance and end bearing, effectively. So when I look at that, I can see that we probably have too much shaft resistance along the bottom elements, or we're making our toe resistance too stiff. So we can try to redistribute the soil resistance in our model. And when that happens, it brings down the shaft resistance a bit, it brings down the peak. We can try to adjust our, and that's a static soil resistance, by the way. When we look at, we can say, well, this is showing us that here that we have too much total force. So our computed curve is above our measured.
The door's locked behind you.
I found that out when I got the pizza, actually. I turned right instead of left, or left instead of right, and discovered the back parking lot. So. Thankfully, the DoorDash guy didn't leave. So that's one of the nice things about Minnesota is everybody's relatively polite. So, if we reduce the dynamic resistance by reducing the dash pot damping value that Travis was talking about on the WEAP side, then that will bring down this portion of the curve at the toe and make that match better. We can also adjust the quakes, which Travis kind of indicated is an indicator of how stiff the soil is. A very small quake means it takes a small displacement to mobilize all of the resistance. And so that's a very stiff soil, like a rock. If I'm on peat, I might be bouncing a lot before I sink in, and so that would be a very high quake soil, a very highly elastic soil. And so here I was a little bit low, so if I increase the total capacity, I can make those changes. And if I look in the late record, I can adjust parameters that affect how the pile is unloading or how the energy is dissipating back into the soil. And that gives me a much better match than the one that I started with. And ultimately, that's what we're trying to do. We're trying to indicate as best we can a model that helps to match what we are observing. So again, the cap WAP and to some extent the GRL WEAP model are similar. We have a shaft resistance for each soil segment. Typically each soil segment is every 2 meters, every pile segment is every 1 meter, and we skip that strictly because for a 30, 40 meter long pile, you'd have 30 or 40 different things that we need to change as part of the doing of the signal match analysis. And so having that makes, or reducing that makes our life easier. You could certainly put a resistance at each pile segment. We also have a spring, a dash pot, and potentially a gap, which is zero resistance temporary free end that is happening at the bottom of the pile. So in CapWAP, we model the magnitude of the static shaft resistance. Again, this is directly analogous to the geotechnical resistance that we're calculating from Nordland or Tomlinson, or one of the static analysis methods. We have our quake, that defines our soil stiffness. Again, low quake, more like a rock. High quake, more like a clay or a peat. So that's the static resistance model. If we look at the dynamic resistance model, something that we've both alluded to is the pile that is loaded very slowly really only encounters static resistance and from shearing and of the soil pile element or the interface. During impact, because we're moving it into the ground very fast, we have both a static component and a dynamic resistance component. So higher velocities mean higher dynamic resistance. And unlike the case method that we used in this morning at the very end of the wave mechanics talk, we have a bit more time to run the analysis. So we used the same model that was used when the wave equation was developed. And instead of relating a velocity to the pile's impedance and a damping factor, the Smith model related it to the static resistance. And so here the dynamic resistance is the static resistance that has been mobilized up to that point, times a damping factor times the velocity of that particular pile segment. So it could be along the side of the pile or it could be at the bottom. They can all be different, unlike the case method. And then we also have a model option that says, I don't want the mobilized static resistance, I want all of it. So that gives you a much higher amount of dynamic resistance right off the bat. So that's saying that the act of driving the pile is really disturbing things and creating a lot of dynamic resistance. And so what that kind of means is if we are using the mobilized resistance, and this is at the pile toe, and if we have a gap which says that there's no resistance until that gap closes, as if the pile is bounced off a rock, then mobilized resistance through here is 0, and therefore dynamic resistance is 0, so you'll have a free end for a longer period of time. And as a result, you'll see a very deep tension response. And then the mix of static and dynamic gives you this envelope of force versus displacement. If we use all of the resistance, then instead of 0 resistance over the course of the gap, we see a lot more resistance over that. So that would be a case where the act of disturbing whatever is down there is really pushing back because it's moving quickly dynamically. But we have options, I guess is the way of putting that, and we can make adjustments to our model for that to happen. So if we are looking at a wave up, remember, quiet period is either the initial impact or the part that's not in soil. This part is our indicator of shaft resistance. That peak is where the toe response starts to come in. That deep tension response is the pile toe moving significantly like a free end condition. And then we see a strong reflection that comes at 2L/C after that from some end bearing. If I use my model for cap WEAP in blue, and I have a very stiff soil modeled at the bottom, then I will expect high wave up relatively quickly after the impact. So there's the pile. There is our static load set curve at the base. And that says that a small displacement takes a small amount of time to mobilize, and therefore we'll get higher resistance in our model earlier. If I model something that is bouncier, say with a quake of 9 millimeters, then it takes more displacement and therefore more time to get all of the resistance back. And so instead of having all of this resistance here, I only have some of it, which allows for this deep tension response to be coming in because we are not getting as much resistance. If we think about quakes, or shaft quakes, this is a large shaft quake. 7.5 millimeters is 0.3 inches. Travis in wave equation said we're usually using something more like 0.1. And that kind of goes to what we saw in the lab today with direct shears. That is, if we do a direct shear test, typically we've mobilized most of our resistance, or we've reached a peak after 1/10 of an inch or less. And I mean, depending on the soil, we can quibble about that on a 5/100ths of an inch kind of basis, but generally speaking, that's what we're looking at. And so what a high quake does is it pushes everything further to the right. If we use a lower quake, it will allow full resistance to start happening directly and more quickly. So we get higher higher values of wave up earlier. If we're thinking about damping, any toe damping will won't have an effect before the 2L/C time. If we have damping that is too high, that means we have too much dynamic resistance, which means we have too much total resistance, which means that our wave up is too much. So if we reduce this toe damping, going from a big envelope to a smaller envelope, then I won't have as much total resistance at this 2L/C time. And as a result of that, I can then get this lower value of wave up. So instead of this amount of force, I'm reducing the total amount of force, which makes it more like a free end, which makes it more like a drop-off. Same thing with shaft damping. Higher shaft damping means we're pushing higher resistance values. So that would be 0.5. If I increase it, it will push more or less everything up linearly, more or less throughout the entire length of the record. When we're doing WEAPs, typically in sands, we are using a lower value in the order of 0.05 seconds per foot. And when we're doing clays, we're using a higher value of 0.2 seconds per foot. And so depending on what you're looking at along the length of the shaft or at the toe, you might decide that you want to use higher values of shaft damping because you're in a more cohesive material, and that would be an expectation for what you're doing in the cap lab model. So all of these things we're doing both manually and automatic when we're running the cap lab. So here's an example of a basic
Yes.
proportional.
Yes.
Any shaft resistance? Yes. Fixed end or free end? Velocity is trending towards 0. Force is rising.
Fixed.
Fixed. If the velocity is trending towards 0, then it's a fixed end. Is it going back to 0 at the end? Yes. The wave up is showing gradually increasing compression followed by a sharp compressive response, which is again corresponding to a fair bit of shaft resistance and a fixed end condition. So everything that we just talked about after pizza before the break about identifying what is good data is ultimately getting us to this point as to whether we want to signal match it or not. The other aspect of this is the 628th blow in the record. So this is an end of drive data set. Usually when we do an end of drive data set, we're interested in something that's fairly high energy that we can try to prove out as much resistance as we possibly can. Excuse me. So this is our first trial analysis. Remember, wave up is an indicator of total resistance. And between 0 and 2L over C, is my wave up, computed wave up too high or too low?
Too low.
Is the blue line above or below the black one?
Below. Right? Below the peak.
Sorry about that. So from here to here,
Oh.
is the
Above.
blue line too high or too low? It's too high. So if I want to make a change to this, I'll need to take resistance off of the shaft, because right now, it's too much. So if I take 1,000 units, I think these are kilonewtons, off of the shaft and put it on the toe, it pushes this portion down and pushes the toe resistance up. And so I can use the intuition that I have from the field, which is, this was a fixed end condition, it was driven to rock, so I know that I should have relatively high resistance. If this works, we're still a little bit too high through here. We're still a little bit too low through there. So if reducing it on this example worked, I'll often do the same thing a second time. So if I reduce that further, another 500 kilonewtons, now I'm 270 on the shaft and 3,100. Now I'm a little bit too low through here, a little bit too high through that region. I could find a happy medium with static resistance, or I could say, well, this seems like a fairly reasonable set of data. Maybe I want to adjust dynamic resistance instead. And so if I increase the shaft damping, remember shaft damping increases dynamic resistance, which will increase the wave up. So if I go back, that's low, that becomes higher, and so now I've tweaked the dynamic resistance on the shaft upwards, and that's made this match a little bit better. I'm still too high in that region, so I could do the same thing with the damping at the toe. If I reduce the toe damping, it will tend to bring down the total resistance. So this is what happens when we reduce the toe damping. That has no effect from the impact to 2L over C, because toe damping can only have an effect once the information from the toe has come back. So there is my peak. We also have a decision to make as to what to do about that little guy. Could be resistance. It could be a change in mass because of a splice. Hopefully we would know that. Here we're using a change in resistance, and so a little weird in that we have high resistance, or low resistance, and a very high value in between. And so that's something you really want to think about if we were presenting this as part of a report as to why that might make sense. Once we say that we are good, we can output. This goes to a graphical output in which we see the measured versus the computed force. Basically what you're looking for as an interpreter of these reports is whether or not those two curves are very similar to one another. So looking here, again, we see they match up quite nicely. There isn't a scenario where the computed force is way above the measured force, especially between the impact and about 4L over C. So that's telling us that things are pretty good in that sense. And then, out at the end, we see some slight differences. And again, that tells us that the match is probably pretty good. See a match quality that's less than 4, or less than 3 actually. So that's pretty good. This is our raw force velocity data. And so if you only have a cap WAP, this is where you can make that that review of the data set that was selected for this particular blow. Given that we have stiffness in the forms of quakes and that we have geotechnical static resistances, if we set the velocity to 0, we can generate a simulated static load set curve. And that is something that we can compare to an actual static load set curve. And then on the other side, we have our shaft resistance distribution, which is giving us from the top to the bottom relative amounts of shaft resistance until we get to the bottom, where in this case we're at rock, so we have very high error. This curve down on the bottom is effectively what you would expect to measure if you instrumented the pile with embedded strain gauges. So if you're doing a static load test with strain gauges that have been sent along the length of it, this is the curve that you would kind of expect to see. We also have a set of summary results. Depth below grade is probably the interesting one. So this would tell us that from 23 to 25 meters below grade, we picked up 75 kilonewtons of ultimate resistance, and that corresponds to about 25 kPa, or about 0.2 KSF of unit shaft resistance. And so we can look at these unit shaft resistances and compare them to what we assumed in the GRL WEAP analysis from our Nordland or Tomlinson methods for drivability. We can also use this unit resistance to double check that things are kind of behaving like we thought they should. The other factors in the model are here. Match quality is 2.7. We are comparing our computed and our observed sets. We also have indicators of the top stress and the compression stress, the maximas. So what's the maximum top compression stress is something that we can compare to what we are measuring with our sensors in the PDA, because those are usually placed near the top. The maximum compression stress can occur anywhere, and in this case is happening at a depth of 26.7 meters, which is the bottom of the pile. Do we we expect high stresses in a pile that has been driven to rock at the bottom. Yeah, we do. And so this result is generally in agreement with what we would expect from the driving scenario that we have. And at 207 megapascal, or which is usually compared to 310 megapascal for steels, it's not at risk, at least on the average, of crumpling at the bottom. And this is a 14 by 89 H pile, by the way. And so what we see is we can use these stresses and this distribution of stresses to our advantage in scenarios where things are crumpling, things are breaking, or things are otherwise having problems. So how do we pick a record? Going back to that question. We want a record of good quality. That means good proportionality. That means no electronic or mechanical noise. We want it to integrate out to a final set or a zero velocity. We want our force to go back to zero, so we're not plastically deforming anything. And if we can get it, we want a short rise time. So sharp.
No.
It is not. Is it proportional?
Yeah.
Very nicely. This is beautiful. A little bit of shaft resistance, not a lot. Our velocity increases and our force drops to zero. So zero force tells us is it a fixed end or a free end? It's like a free end. But if looking at our wave up, we see the indicator in tension of the free end, followed by a big compression response that's late. So this is telling us that this concrete pile is pushing into something a little soft, and it pushes in a little bit more, and then when that happens, the soil pushes back. So this is similar to what we would expect the result of end-bearing in sand to look like. So the pile toe has to move, but once it moves far enough into that material, the material really pushes back. It's not a fixed end, but it's also not free because eventually we get end-bearing. New things return to zero. Here they do, but there not so much. So we may need to look at this more carefully. And so, proportionality is good, the integration is not so good. So in other words, it's not kind of falling out to that final set. If I go to the last blow, this one had an energy of 73 foot kips. We're at 69 foot kips, so even though it's the last blow, it doesn't seem to be shutting off and only giving us about half the energy. Proportionality is still good. The integration is coming out to what we observed at the end, and so it's much better. Also because the force and velocity are returning to zero at the end of the record. So that's all very good. When we select a record, we want, we don't really know whether we're out here or not. If we don't move it enough dynamically, there's probably more to be had as well. And so making sure that we hit it hard enough to try to mobilize things makes a difference. Did I?
No, you're right.
Okay, you got it? Okay.
Yeah.
But that's the concept. We want to make sure that things are moving. Similarly, setup time restrike testing is often performed a matter of hours, sometimes after driving. So if you're not sure if there is setup, sometimes a pile tested in the morning can be used for a pile to restrike in the afternoon, just to see how much things are changing. Typically, it's 1 to 10 days after installation. And of course, the engineer in us wants the right answer and the most resistance, which would put us somewhere out here in time. The contractor in us doesn't want to wait at all. And in fact, would rather have the answer before they put the pile in the ground. And so Oftentimes, this 1 to 10 day range is kind of a happy medium. That doesn't mean that you can't design certain types of pile test programs or staged type construction such that you drive some piles for stage, that moves the pile more than 1/10 of an inch. Sometimes though, the hammer isn't big enough, the pile is really long, there's a lot of setup, or all four. And so we may have a scenario where it's a really long pile, there's lots of setup, we have end bearing layers that we're interested in, and the hammer is a little small. Yes, sir.
Well, I think we tell them to qualify the hammer by 165%, so they're just
Right.
meeting our criteria, not going for.
And that's good, unless you get a lot more resistance than you thought you did.
All right.
Which is a great problem to have usually, but you know, it means that you probably leave some money on the table in terms of a pile that's a little long. So this is an example, again, out of Florida. It's a closed-end pipe, driven with a diesel hammer, 148 feet long, cross-sectional area is about 37 square inches, so fair bit of steel. It's 148 feet in the ground, long, 115 feet in the ground, so it was driven in the St. Johns River, which means that there are there's some stick up above the water, and there is some stick up in the water, which is not contributing to resistance. This is the end of drive data. So knowing what we now know, is it a diesel hammer?
Yes.
Yes.
Yes, I said it right there. So, but we can also see the pre-compression. How's proportionality? Very nice. Any shaft resistance? Yes, and we can see that in our wave up curve as well. Is the pile toe moving?
Yes.
Force is dropping to zero, so zero force. Velocity is increasing, so pile toe is moving. It's not truly a free end, but we have a deep tension response showing that this closed end pipe is moving. And you'll take my word for it that everything goes back to zero. And so when we look, our resistance values are on the order of 350 to 400 kips. This was driven in, I think, late August, and they got back on it a little over a month and a half later. This was part of a test pile program. They spent some money putting in closed-end pipes, pre-stressed concrete piles, and some H piles at different points in the river, trying to provide for a design build set of bidders the data so that they could figure out what the best way to go about it was. So this was in August. We came back in mid-September, and let's take a look. Still a diesel hammer, still proportional. Is there shaft resistance? Is there more shaft resistance? Let's go back.
Oh, yeah.
That's where we started. And if we let's look at the wave up here. That's where we started, and that's where we are now. So same length of pile, but we see the wave up really jump because we waited that amount of time and because we've given a highly disturbed soil profile a chance to dissipate those pore pressures. And we see more separation between force and velocity. We see our Rx capacity values, that's the case method capacity that we talked about with a JC of 0.5, 0.7, and 0.9, is now between 600 and 900, coming off of 350 to 420. This is the very first high energy blow. But remember, this pile is 115 feet in the ground, very long, and the displacements are going back to zero at the end of the record. So it's not really moving. If I go to the fourth high energy blow, and you'll take my word for it that everything in between is kind of gradually changing in the same way. Again, looking now down here, we see that that has jumped up quite a bit. Looking down here, we see that that's stayed the same or is approximately a little bit lower. And we see that we went from 38% and 45 kip feet of energy to 55 and 46% energy. So the hammer is starting to warm up and stroke a bit more. And what we can see is, this red wave up curve has now jumped up some more. So what happened? We've actually started to, we got more energy into the pile, more force into the pile, and now we're starting to move that lower bit of the pile. So this is the 6th high energy blow, and you can see it jumping up a little bit more near the toe. You can also see, if you look here, that's staying pretty much the same. This is the result 200 blows later. So going back, there's our shaft resistance. We see that it's dropped down. So we partially redisturbed the soil. And that partial redisturbance has now lost some of our shaft resistance. However, when they drove this, they knew there was a sand layer from driving adjacent piles. So they said, wouldn't it be nice if we hung it up above the sand layer, or in the case of potentially a Minnesota scenario, we hung it above that weathered sandstone layer that we can drive into a bit, but wouldn't it be nice if we hung it up, waited, and then drove it deeper into this shaft or into this end bearing layer? So 200 blows later, they did that. We can see this little bit of a tension response, which if I can stay still enough, is that little guy right there. So that tells us that we're at the end of the pile, and that this is the mobilization of end bearing in that sand. So, which blow do I cap on? If I did end of drive, that would tell me probably not a lot, just what the resistance was when I stopped driving. If I did the second blow, I'd get pretty good resistance in the upper section, but under predict the lower one. If I did the fourth blow, that's probably pretty close, so that's 1,000 or 800. The next blow is 898, and then this one is now 949. So we could do just one and try to pick the highest value, or we could do them all. And that's where the superposition idea came from. You need to be very careful about it when you're doing the cap lap, so that you're not double counting things and allowing resistance to move down below to the next level when it's really in the level above it. But if we carefully cap lap several of those blows, then we can develop an envelope of shaft resistance. So these are the highest values from that first high energy blow. These are the highest values from the 6th high energy blow. And that is the resistance from that sand layer. And we can take the sum of these and the sum of these and the sum of that and call that an approximate overall resistance for this pile. Now, is this all that common? Not really, because you need a very specific set of scenarios. What we will often sometimes do is, if we see a refusal blow count at the end of drive, and we didn't think to hang it up, we'll do the cap up on the refusal high end bearing blow count at the end of drive, and if we can come back and do a restrike, What we might see is that there's higher indications of shaft resistance. And those higher indications of shaft resistance, we can then add to the end of drive by end bearing. Because we're able to mobilize things up high more easily on the restrike, and we will be under mobilizing what's happening in the rock down at the bottom. And so a more common way of doing superposition instead of the kind of the crazy one from the long one that we're looking at here is to just take the end bearing in rock from end of drive and add shaft resistance with an under mobilized toe from the beginning of restrike, and that gives us a chance to squeeze out a little more resistance if we need it. Of course, we can't do that if it exceeds the structural capacity of the pile. So, you know, there's that consideration that we have as well. This is easier and very likely more accurate when we have steel piles. So we remember the very first slide after lunch, maybe the pizza was setting in. The very first slide after lunch, we had really sharp impacts on the steel and wider impacts on the concrete. And so for steel piles, or for driven concrete piles that have stiffened cushions because they've been driven for several hundred blows, we probably do pretty well. Drilled shafts are a lot more difficult. In other words, they have wide input force pulses, and they have uncertain cross sections versus depth. So you may have places where cave-ins have occurred, you may have places where the concrete head is pushed out into softer soils. And anytime you have a bulge, it looks like additional resistance in the wave up. Anytime you have a reduction, it looks like a drop off in resistance in our wave up. Here, because this is very sharp, the time between our drop and wave up, the beginning of the toe response to the peak of the response coming back is really short. So we don't expect to have missed a lot of shaft resistance where things are on top of each other. If we go to the beginning of that restrike, it becomes less clear where that toe response is. So it would be harder to separate out shaft resistance from end bearing in a scenario where you're not getting all of that toe response. When we get to the very end of that restrike though, and this is again that same data we just looked at, we can see that tensile reflection at 2L over C. That defines the transition from shaft resistance to end bearing, and it allows us to be a bit more confident in our distribution between shaft resistance and the bottom. We still have a fair bit of uncertainty in that last modeled element. So at the very bottom of the pile, we have a 1 meter segment that has resistance along the side and also resistance coming at the bottom. And that's really a big mix. And so we try to reduce the uncertainty by being consistent with previous elements above it. That keeps us from putting too much on the shaft. And in harder, weak rock, as the pile penetrates, it tends to generate friction and end bearing. So here's an example of that. Diesel hammer? No. Proportional? Good enough. Any shaft resistance? And then all of a sudden, the force goes way up, the velocity goes way down, and our wave up is significantly in compression. That's telling us that if we didn't know better, we'd probably say this is the fixed end at the bottom of the pile. But what's happening here is we're getting a lot of resistance that is happening. Well, there's the cat flap result. 42-inch diameter pile. We have 24,000 kilonewtons, 24 meganewtons. That's about 6,000 kips at the bottom of this pile. And we see about 600 kips in the last few elements. And so what the owner of this does is says, for computing tensile resistance or tensile uplift resistance, I don't trust these because they could just as easily be in the end ring. So there are ways that if you need the shaft resistance very clearly, we can choose to ignore certain things to take a slightly more conservative tack. Now the other downside of this is we have beta markers at this point, and we can see a very strong end bearing component. We would interpret that as having a lot of end bearing, as having a lot of resistance down there, and it does. But when they tried to drill it out, because they wanted to go deeper, well, the bottom was a little bit elliptical. So instead of a perfect circle, it had gone from something like this to something like that, which is a problem to get a drill down there, but for the purposes of the PDA, the amount of impedance hasn't changed. So we don't see an indicator of reduced impedance because it really hasn't happened. Second, we don't see that very clearly because there is so much resistance overwhelming it. And so sometimes if you are driving piles to rock, and I've seen it recently in Ohio, then deformations in the flanges of an H-pile are just something we can't pick up with the way that PDA works. If the pile gets shorter, that is, and gets crumpled up, that is something that we can find. So with that, we hit 245.
You can see that much positive in the velocity. You can see the force dropping off there pretty clearly. Pretty pronounced break in your wave up prior to the toe. Here we continue to drive almost another foot, and we are clearly damaging it much worse at this point. Pull the pile out, and you can see big, massive kink in it. I'm surprised they got this out, though. I was actually sort of questioning if I had the right photo because I saw it was 75 feet in the ground. It's usually pretty deep to pull those out.
Does everybody see what we're pointing at? On the wave up curve.
Wave up, braking at the appropriate time, the tool lever C marker. Wave up, braking before the tool lever C marker. Not absolutely pronounced compared to this. And that marker is, when you see damage, this is what you see, that not only does it get more pronounced, but it keeps moving up the pile, right? The damage is like working its way up the pile as you continue to drive it downwards. So pretty smashed up bottom of the pile. Here's some more. I have a handful of data that's almost all the same thing.
What were the beta factors on those? Or
Toe beta. Do you want to explain toe beta and why it doesn't have a value?
In the mic.
Oh.
So it's hard to get a sense of how much it's changing because we get a number in beta. We are looking at how much that dips down to a peak. And at the toe, things are superimposing upon one another. And so the reflection from the toe is going way down deep. And we expect that, and so we don't calculate a beta because it's the end of the pile. And when those two things start to superimpose upon one another, we can't get a good beta number so close to the bottom.
How far above the toe does it stop making a beta marker? Do you know?
I should know. I think it's like 10% of the length.
Okay.
It might be 5.
So shortly, if we had kept driving, you would start to see like stacks of markers. So then it would have said there's a beta marker at, another. It would give you a proper beta somewhere close to where you have that toe beta marker. So like I said, I have more files where it's all the same thing, where you can sort of gradually see those breaks in the wave up. So instead, I just skip to the good part.
but you weren't changing the impedance, or were you?
No, we're not changing that, right? So we are driving one of these piles, and you can already see there's not a beta marker here. This is a splice that we put in the PDA, right? So we were already suspicious of this this occurring, so we've got a marker exactly where the splice is. So within the PDA, you can mark where any splice is, so you can keep your eye on those questionable locations. So, and I think there's another splice shallower as well. We drive a little deeper, and now we see a big opening, or a big break in our impedance. And this was really concerning because we are only at 4 blows to the inch. So this wasn't hard driving. No, we hadn't gone through hard driving. There's no reason to have this splice break. It wasn't really, didn't have any excessive stresses delivered to it. There's another blow where it comes apart even further.
So can you go back real quick? Is there a rule of thumb that if some of these blue and red lines cross at certain points, it's bad?
Well, when your blue velocity goes positive, your force goes negative. The difference between the two is what you're looking at on the bottom. So there's that big dip in the wave up, which is your impedance reduction. So this is one and the same. I mean, Brent's describing it much better, but for a lot of us, we're really just focusing on the wave up as we drive. But
So what comes after 2L over C, you're not just concerned about that?
oh, this is that what you're talking about?
Yeah.
Well, the blue is the displacement on this lower one. You're asking about that blue trace?
Well, maybe up above when those, they crisscross.
Oh, when they're crisscrossing out here beyond 2L over C, I mean, that's an end-bearing response. Nothing strikes me as abnormal.
What's happening at 34? Jeez. That crossover is what is important.
Okay.
Right, yeah. But these out here in the end-bearing response, I don't know what that.
All right.
that means much of anything. So this, what you see here on the left, this was a video. So this is the welds that the welder was performing. This is not the weld that broke. This is another one of the welds that he had done. You can see that another welder is coming, and there's a series of these little markups he's put where he's not so happy with those welds. And here is welder number 2's weld, actually that same pile. So they rooted all this out, cleaned it up, and he did it again. The big concern with this splice, so this splice was damaged, we replaced it, but he had also spliced some of the reaction piles of the static load test. So now we're running the static load test, and 2 of these 4 piles have Mr. Suspect splicers or Mr. Suspect welder splices not very far below the ground surface. So we're somewhat scared to run this static load test. So what you can see here is we cut off a piece of pipe and we welded it on to this base plate. So our entire jack stack is protected in that pipe section. We just have a cutout in it so we can see what's going on in there. But the danger would be if splice gives, everything shifts, and our jack and load cell and everything gets thrown one way or the other. So this is the solution they came up with to protect all of us during this load test. Now, I've seen other versions of cages around the jack and load cell before. As it turns out, this pile didn't get loaded all that heavy, so it wasn't simple. Didn't even really move much significant one way or the other. But a very clear indication of damage at the display. So. We had to speak up to.
So what we sometimes see with open piles is an abrupt increase at the base where the plug is developing. And so this looks like resistance, and it partly is resistance, but it's also soil towards the bottom that's really pushing against the side. And so we don't tend to see these types of sharp increases in closed-end pipes. When we're looking at open piles, especially 24-inch open piles, where this is the behavior of the soil sitting inside the pile. So part of that will be modeled as resistance, and part of it gets modeled as additional mass, or as additional impedance, basically. As those piles get bigger and bigger, these types of things become less common unless the soil gets very dense or very stiff. And then it tends to go along for the ride a little bit better. We tend to see this on early blows more than on later blows. And so if we're doing open-end pipes, it's not a bad idea to not try to hit it with a 10-foot stroke right off the bat. It's better to try to dial it back with either a hydraulic hammer or with a lower fuel setting to try to see if we can make that happen, because that will give us more resistance. And going back to what Travis was saying, that additional resistance will start to go away dynamically, but it will likely show up statically. And so Dan Brown and Associates, probably 8 or 9 years ago, did some conceptual modeling in a NCHRP report that looked at some of the complexities of open-ended piles, and that was kind of one of the things that came out dynamically. And when Frank looked at that in the wave equation, Frank Rauscha, he kind of noted that this soil here has an inertia, and if we can get it so that the resistance forces are less than, or bigger than the inertia of that pile as it's being accelerated, we can get a plug. But if this is accelerating quickly, the plug doesn't want to move. It wants to stay at rest. And so that's when you get a resetting of the coring type behavior that comes out of that. And so that's part of it. What happens out on the end bearing and how one models that in signal matching is also something that gets debated a fair bit. And we'll often do that with an extension of the CAPTAP model called radiation damping, that lets some of the soil around the outside move a bit as well. Either whether it's in the plug or whether it's outside of it. So that's something else that sometimes pops up in open piles, especially in scenarios where the open pile and the static load tests are agreed. So that's what came out of Kentucky Lakes, I think. And part of those were non-restrictor plate open-end pipes, and some of them were restrictor plate open-end pipes. And having done probably a half dozen of the restrictor plate type jobs, I don't recommend them because they never behave quite like you imagine they will. It's one of those things that if you need to do it, you probably need to do it, but you're likely embarking on a research project that you aren't necessarily knowing you're getting into, because everybody has their own design for restrictor plates, which again are usually a plate with a series of holes in the middle that are reinforced inside these large open-end pipes. And the idea is that you're going to induce more direct end-bearing force on the plate. But oftentimes what we think happens is stuff gets trapped in there and behaves more like a mattress than the hard end bearing result from a gravel layer that you thought you were gonna get, or from rock or from something else.
We had a project in southern Illinois where we cut them out after the first couple piles, cause the drive times took forever. All of that material at the constrictor plate relaxed, right? So it looked like we have a lot of capacity. The restrike would show a big loss in capacity, or basically whatever that plug that developed into the constrictor plate, gone. So this went on, and it was 20 more feet to rock. So it's like, just hack them out, let's go to rock, get your capacity easily, and be done. So, which is what they did.
And so if that open